Section 10.10, Computed Tomography. We'll start with an orthogonal projection formula to help us find approximate solutions to overdetermined systems of linear equations. Let L be a line in R2 with equation A transpose x equals b, and let x star be any point in R2. So x star is just anywhere. Then the orthogonal projection xp of x star onto L, so we'll project and we'll end up with xp on L, is given by x star plus b minus a transpose x star over a transpose a times a. Let's use this to find an approximate solution of the linear system given over here with L1, L2, and L3, shown in this figure, right over here. So what we'll do is we'll write each of our equations using matrix form. So I'll write L1 as A1 transpose x equals b1, and I'll write the second equation A2 transpose x equals b2, and then A3 transpose x equals b3, where we have x is our solution equal to x1, x2. We'll have to figure out what that is. And then A1 is given to us as the coefficients for the first equation, so that's just 1, 1. Then A2 is the coefficients in the second equation, so that's 1 minus 2. And A3 is then just 3 minus 1, where B1 is what the first equation equals, so that's 2. So then B2 is minus 2, and B3 is 3. What we want to do is we want to take an arbitrary point, x0, project it onto the line, and then we'll figure out what that point is, and we will then project that again, and get another point, and then project again, get another point, and so on. And we'll just keep projecting that way, and we'll go around and around and around and around, and eventually we'll end up with this limiting cycle of projections where we just keep projecting back and forth to the same 3 values. And we'll use any of those 3 to approximate our system. So let's start with our first one. In general, our formula is going to, for the projections, is xk p will be equal to the previous one, xk minus 1p plus bk minus akt, ak transpose, times xk minus 1 p divided by ak transpose ak, and we'll multiply by ak. Okay, so that means we'll do that for k equals 1, 2, and 3. We'll start with an arbitrary point, x0 equal to 1, 3, how about? And then we'll figure out what x1, 1 is. So that'll be 1, 3 plus the first b for b1, that would be 2, and then we'll subtract a1 transpose, so we're subtracting off 1, 1 times, we need to do xk minus 1p, so that's 1, 3 again plugged in, and we'll divide by ak transpose, so that's 1, 1 times ak, so that's 1, 1, and multiply by ak, multiplying by 1, 1, and if we simplify that, we'll get 0, 2. Okay, so let's organize ourselves a little bit with a table. When we have x0 equal to 1, I'll do 5 decimal places, so 1, 3, then that'll be our x1, that'll be our x2, and then we'll have x11 equal to 0, 2, so that's 0 with 5 decimal places, and 2. So then we plug that in, we project again, and we'll get x21, which is 0.4, 0, 0, 0, 0, and 1.2, 0, 0, 0, 0. We project again, and we'll get x31. Just plug it in again, and you get 1.3, 0, 0, 0, 0, and 0.9, 0, 0, 0, 0. And then when we project again, we'll end up in our next cycle. So we'll be in cycle number 2 now. So I'll restart with x1, but now I'll go up to number 2 because we're 3 different equations, so we're cycling around and around and around, and we'll start getting around every 3. So x12 will be 1.2, 0, 0, 0, 0, 0.8, 0, 0, 0, 0. x22 will be 0.88, 0, 0, 0, 1.44, 0, 0, 0, and x32 is 1.42, 0, 0, 0, and 1.26, 0, 0, 0. So that's our table for our first 2 cycles. So if we want, we can keep going, try to find the limiting cycle. So let's start with our 3rd cycle. That'll be x13 now. And we'll get 1.08, 0, 0, 0, and 0.92, 0, 0, 0 for x1 and x2. Then for x23, we'll get 0.832, 0, 0, and 1.416, 0, 0. Then for x33, we get 1.408, 0, 0, 1.22, 400. Okay, so as you can see, we keep doing these, we get more and more cycles. We're kind of getting closer and closer to what would be the point of intersection if there was one, the center of these lines. Let's keep going to the 4th cycle now. So x14, so that'll be 1.09200, 0.90800. x24 is then 0.83680, 1.41840. x34 is 1.40920, 1.22760. And now we've finished 4 cycles. So how about we do 5 and 6, and we'll wrap up there. So for x15, we have 1.09080 for x1, and 0.90920 for x2. So you can see that the x1s now aren't changing much anymore. They're basically 1.09, 0.09, or 0.9. The x2s similarly are starting to kind of level off. We get 0.83632, 1.41816, and then x35 is 1.40908, 1.22724. And last but not least, we'll stop after 6, so x16 is 1.09, 092, 0.90908. x26 is 0.83637, 1.41818, and x33 is 1.40909, 1.22728. Okay, now that our tables are done, in general, we could see that the limiting value for x1 is 12 over 11, 10 over 11. For x2 star, it's 46 over 55, 78 over 55. And for x3 star, it's 31 over 22, 27 over 22. And any one of these could be used as an approximate solution to this system of equations. Let's now find the unknown pixel densities of the 9 pixels arranged in the 3x3 array illustrated in the figure. These 9 pixels are scanned using the parallel mode with 12 beams whose measured beam densities are indicated in the figure. So we're trying to find unknown pixel densities in order to, for example, construct a slice, like a scan from a CAT scan machine, where you project a whole bunch of beams onto pixels, and you have to try to figure out pixel densities from an overdetermined system, and then use those to construct a two-dimensional image. So we'll start by writing out our system of equations. So how about I'll write the bottom one on top with the x7 first. So for number 7, so x7 plus x8 plus x9 has to equal 13, because B1 is 13. x4 plus x5 plus x6 has to equal 15. And x1 plus x2 plus x3 has to equal 8. And then we'll similarly do that for the second figure. So we'll get x6 plus x8 plus x9 with the bottom row. That would have to equal 14.79. Then x3 plus x5 plus x7 has to equal 14.31. x1 plus x2 plus x4 has to then equal 3.81. Okay, let's now how about we do the last column. So I have x3 plus x6 plus x9 equals 18. and then x2 plus x5 plus x8 equals 12. Right, just the middle. You have to adjust what you're adding up depending on where the beam projects, right? So the 689 and the 357, etc., etc. So just did 258, so now I'm doing 147. So x1 plus x4 plus x7 equals 6. Okay, let's keep going. For the last one, we'll do 2, 3, and 6 for this arrow. So x2 plus x3 plus x6 is equal to 10.51. Then x1 plus x5 plus x9 is equal to 16.13. And x4 plus x7 plus x8 has to be 7.04. So now how about we choose our starting point to be x0 equals 0. And therefore x1 using our projection formula will be just a whole bunch of zeros added to 13 minus a whole bunch of zeros, 1, 2, 3, 4, 5, 6, and then 1, 1, 1, because we have 7, 8, and 9. And then we'll multiply that by our starting vector again, bunch of zeros, and we'll divide by 0, 0, 0, 0, 0, 0, 1, 1, 1, and multiply by 0 through 0 with 3 1s at the end. And then again multiply by 0, 0, 0, 0, 0, 1, 1, 1. So what we'll do is that'll give us our x1. I'll put it in the table. I'll just I'm only going to write this calculation out once, and then I'll keep doing it, iterating, throwing in the new vector each time, plugging it in, and generating the table. So starting off with x0, that was the 0 vector that we started out with. So this is for x1, x2, x3, x4, x5, so I need x6, x7, and x8, and x9. So then by computing x11 using this calculation that we wrote out, we'll get 0.00 for x1, 0.00 for x2, 0.00 for x3, 0.00 for x4, 0.00 for x5, 0.00 for x6, but then x7 becomes 4.33 because of these ones that multiply through and add, and x8 is 4.33, and then x9 is 4.33. So then we do it again, plugging in x11, and we'll get x21 is equal to 0.00, 0.00, 0.00, 5.00, 5.00, 5.00, 4.33, 4.33, 4.33. So then let's keep going, because we have to go through 12 different numbers to get through this entire cycle. So for x31, we'll get 2.67, 2.67, 2.67, 5.00, 5.00, 5.00, 4.33, 4.33, 4.33. And now we can do x41. We'll get 2.67, 2.67, 2.67, 5.00, 5.00, 5.37, 4.33, 4.71, 4.71. For x51, we'll get 2.67, 2.67, 3.44, 5.00, 5.77, 5.37, 4.33, 4.71, 4.71. And then for x61, we'll get 0.49, 0.49, 3.44, 2.83, 5.77, 5.37, 5.10, 4.71, 4.71. And we'll do x7, and we'll just keep going like this until we hit all 12 in the first cycle. Now that we've finished the 12 different pixel densities for the first cycle, how about we look at the second cycle, but I'll just write out the 12th density in the second cycle because we can use any of them as an approximation, so I'll just use the 12th. So 2.03, 0.69, 4.42, 1.34, 7.49, 5.39, 2.65, 3.04, 6.61. And then if we kept doing this, when we get to the 45th cycle, then x12, 45, it turns out would be 1.32, 0.60, 5.32, 2.15, 7.49, 4.59, 1.76, 3.14, 7.32. And there's our table of pixel densities. It's a fair bit of work to determine it, but not if you have a computer that you could just plug this algorithm into, and then it can just generate these numbers, and then you just tell it where you want to stop at, and then there you go, you have your approximation.